Thanks, John. So let me join the previous speakers in thanking Andre for such a great job in organising a fascinating workshop. I've learned a lot, really, great stuff. And also to thank the organisers too for the program in general, which has been very interesting. So this talk, yes, as you'll see, is a very applied talk. It's going to have a little bit of complex analysis and a little bit of computation, though it won't have any computational complex analysis, unfortunately. It's joint work. It's joint work with Robb McDonald, Ollie Southwick, and Sean Jamshidi, who've all passed through UCL at some stage. So the problem, or the observation, is this is a picture of the outflow from the Hudson River, and the colours give you temperature of the water, and in particular, the warmer the water, the less dense it is. And so this is warm, less dense water, and it comes out of the Hudson River, and it turns right, and it runs down the coast here. And they've taken measurements, they know the sort of speeds it runs down there. And so the question arises, why does it turn right? At what speeds does it go? How wide is the current? Things like that. Well, you probably know why it turns right. It turns right because the Earth's spinning, and therefore in a non-inertial frame, and therefore its Coriolis force will push it against the wall. And that's true even for a linear flow. It doesn't need any nonlinear dynamics. The usual surface water wave, the lowest mode, is pushed against the wall by Coriolis force, a Kelvin wave. And so we'll always have this Kelvin wave in our problem. But is there more to it than that? So here's there's a very nice full-scale experiment done here in about 5 years ago. They removed a dam up this river, and then the water rushed out, and it formed this plume, which, as you see, turns to the right. And the question is, can we predict the shape of this plume here? People do experiments on this. It's a very important problem in a way, because this outflow problem. So there've been a lot of experiments being done. You do them in a rotating tank because you've got to simulate the Earth's rotation. You've got to have strong Coriolis force. In fact, the Coriolis force in a way has to dominate everything in the problem. And what they see here, they put a sponge here and they pumped light, dyed fluid out, and it formed a current which ran around the edge of their tank, and then of course they stopped. Here's a numerical simulation of a similar problem done with an ocean model, in fact, in a circular domain. Again, they get this blob and then a draining current running around, which in a way, if you notice, is different from what's observed in the ocean. So another question is, can we give an explanation of why in an experiment you might see these blobs as well? Okay, well, what are the governing equations? Here are the governing equations. I'll just throw them at you. I think many of you will be familiar, well, some of you will be familiar with these. These are the so-called rotating shallow water equations. In a particular case, they're the case where the flow is sufficiently slow that the Froude number associated with the surface is small, and we can take the surface to be rigid. There's an interface, which is down the way it's drawn here, a depth h, which is a function of x, y, and t. And then this has got density rho 1. There's an infinitely deep layer of density rho 2. And so, because it's infinitely deep, to leading order, its velocity, it's a stagnant layer. And what we'll discuss is the dynamics of this layer, of this interface here. So those are your governing equations for the velocities u and v in the upper layer, and h, the thickness of the layer. they're actually, I think you know, they're isomorphic to the compressible Euler equations. And they have all the same features of the compressible Euler. The conserved quantity in here, which is like the pointwise conserved quantity, they're two-dimensional equations, there's no z dependence. So that the quantity that takes the place of the vorticity is the so-called potential vorticity, which is the absolute vorticity, that is our relative vorticity relative to our rotating frame, plus the rotation of the frame itself to give you the absolute vorticity, and then divided by the thickness of the layer. And this is the conserved quantity, just like vorticity is in 2D Euler. There's our relative vorticity. So there are two classical limits of these equations. The one I'll talk about today is when the vorticity, due to our motion, is small compared to the background rotation. This is known as the QG limit. There's another limit, and that is the so-called semi-geostrophic limit. And the semi-geostrophic limit is when we go very long in one direction, but short in the other. The QG limit knocks out all the coloured terms. And the SG limit just knocks out these ones here. So in the QG limit, if you notice, we just have this balance here, so-called geostrophic balance, which really says that H gives you a stream function for the flow. So our surface elevation or thickness is the stream function for the flow. So all we need is we've got a stream function here, and we've got conservation of this quantity, and that's our equations. And they're, of course, fully nonlinear. I'll look at two cases. One case is when we have, here's our ambient layer out here of density ρ1 sitting above our quiescent layer. Well, suppose that we have an inlet which is shallower than the ambient layer. So when the fluid moves outwards, it has to stretch slightly. It's rotating, so when you stretch it, it's going to spin faster. And so we generate positive relative vorticity. So this will be a positive relative vorticity. Pi is the sign of the vorticity, so this is positive relative vorticity, and we're looking at the dynamics of this interface. The opposite case is if the inlet happens to be deeper than the ambient, then we can get a squashing of the fluid elements. That gives us negative relative vorticity. They now spin slower. And so we've got our opposite case is that the outflow fluid has negative vorticity. So it's a 2D problem, so we can now work entirely in 2D. So here we are just looking down on the flow. Here's our wall. Here's going to be our source region where the fluid is coming out. We've got a current coming out of here. This is the ambient out here, which was initially at rest, and this is the fluid that we've expelled. And let's take the boundary between the two will be this curve C, which in the long wave limit, if it doesn't overturn, we can just take it as capital Y of x and t. So what are the governing equations? Again, we're going to go straight to the so-called QG limit. So as we said, the interface displacement gives a stream function. So there's our stream function for the flow. The governing equation, that PV is just, in fact, the Laplacian minus the elevation. So it's a Helmholtz operator, modified Helmholtz, and it's equal to a constant in D. It's either equal to 1 or minus 1 for negative vorticity. And outside D, the fluid hasn't changed, so it's 0. We've had to scale actually on the flux coming out divided by the vorticity to turn this into 1. And there's one parameter in the problem, this A that's appeared. It's a measure really of the density, the importance of density in the problem. It's the so-called Rossby radius, the long wave speed divided by rotation times our length scale. So I'll take that event initially to be infinite. When we take it to be infinite, so it's weak density effects, this drops out, and this is the Laplacian. And this is identically the Euler equations, the 2D Euler. So we're just solving the 2D Euler. And then we'll come back and we'll look at it with finite A. What are the boundary conditions? Well, we just say we know the velocity on the wall. It's what's coming out of the source. And so it's 0 where there's a solid wall when x is bigger than w, and between minus w and plus w, it's some function we've specified, some velocity profile q dashed. We can integrate that up, and we actually know the stream function along the wall. So we know the stream function along the wall, and we know the governing equation. So therefore, at every instant, we can work out the velocity field. There's no time dependence. It's just entirely known. It's just for the Euler equation to be inverting the Laplacian. And once we know that, we've got the velocity field. We can substitute that in and use that to drive around that material contour. So the only dynamics in the problem is the position of this material contour, which is being driven around. You know it at its new position, you invert the Laplacian, and then you move it on again. And there's a very well-established technique for this, so-called contour dynamics, which is everything is just moved into a one-dimensional problem along the interface. And we'll use that as the test for our solutions, because there are no further approximations to fully nonlinear solution. So let's have a look at the vorticity-dominated flow. Let A go to infinity. As we said, the vorticity equation just becomes Laplace's equation. The governing equations are precisely the 2D Euler. And you can get a parameter-free solution for the outflow. So let me show you, just to remind me to show you a movie. If I can do this. A movie. Oops. Oh, I know. Oh. So here's a movie of, there's a source at the origin, at the wall. The fluid is coming out, fluid of vorticity 1. It's seeing image vorticity in the wall, and it's moving along the wall. And so this is the outflow. What you could see is that the scale there is very stretched. I think it's 30 across the bottom and only 3 up the top. These waves are very long. If we can use that. And in fact, there's a standard method that will let us find an exact solution for that. And I'll show you how we can do that in a minute using the hodograph plane. And this is just a comparison of that analytical solution with that time-dependent integration. And you can see it does eventually approach that. And you can also see how long these waves are. They are very long waves. So let's have a look at this and see if we can also build in this blob. So what we've done is we've taken the source that we just had on the wall, but we've also added a doublet. So we've added a point vortex just inside the flow, which is driving the flow in a clockwise direction, and an equal and opposite point vortex inside the wall, driving it the other way. And then we've let the two approach to go together to give us a doublet, so there's no flux through there. But there's a source at the origin, and there's a vortex doublet at the origin. So how do we solve this? Well, we psi is 0 on the wall, so psi is 0 all the way around here to get a steady solution. So therefore, the flow satisfies Laplace's equation out here with 0 on the boundary, so it's identically 0. So therefore, for a continuous solution, the gradient of phi has to vanish all the way along gamma. So we're going to try and find a solution. The gradient vanishes on gamma. And then what we could do is we just introduce a particular solution which has unit vorticity in the region D to get rid of the vorticity in the fluid, plus a solution with no, plus, this is the particular solution. When we add it to our solution, we get a solution that has no vorticity, an irrotational flow. And so this W we've introduced is an analytic function in D. And in fact, it has the property that when U and V vanish on the boundary, W0 is simply Z bar. So W0 actually is the Schwartz function for this curve here. So our problem reduces to finding the Schwartz function with a specified singularity at the origin. This method was introduced, I guess, by Sam Howson and John King. So how do we solve it? Well, we actually use a slightly different function, this, again by Sam Howson. We add z onto that function, and this is going to be our function. U and v were our original velocities. Here is our linear shear flow, and this is our irrotational flow here. And now you can see when u and v vanish, it tells you that u1 is y on this boundary, and v1 is 0 on the boundary. And then the standard method is to do this now in the hodograph plane. So instead of solving for w as a function of z, solve for z as a function of w1. And so that's going to map this, our flow field D, actually into the whole plane cut along this line here. And I think you can see that if we start off at the origin, that's where the source is, so the flow, so w is infinite there, and we're out here. Then we go along here, y is 0 along here, and v is 0. So we move in along here to the first stagnation point. Then we start moving up gamma, but on gamma, v1 is still 0, but u1 is y, so we've got y as u1. We move up until we get to the thickest point, and we've scaled that to be 1, y equals 1. And now we are on the positive side because inside here the velocity v1 is positive. Now v1 turns negative, and so we move on to the other side of the plane, and we move, u decreases now until it gets to capital A here, and there, let's say that the current has thickness alpha. So u decreases again until we get to A, where it has thickness alpha, jumps over to here, and then it moves along here with y equals 0 to S2, and then y equals 0 back to the origin. So we've mapped this domain D into this cut plane. Here it is again, here's the cut plane. Here's our problem, solve the Laplace's equation in this cut plane with this specified values along the plate, and with a condition at infinity that gives a dipole at the origin, and this is the condition at infinity that does that. So this is an easy one to solve now, of course. We just open up this angle here with a square root. So we open it up at u equals I, and with this square root singularity, with square root mapping, we turn it into the upper half plane. Here we are now, we've got a problem in the upper half plane, and we know y is 0 along to here, y is u1 from here to here, and then y is 0 again. And in fact, you could solve that just by inspection. It's just this Cauchy transform, if you like. It's this thing that Sheehan's been talking about. Here's our log w's, and then this is just the function that we want. It's correct, except we can add on an arbitrary function that's analytic in the upper half plane, and which has vanishing imaginary part along the plate. And now we just apply the far-field boundary condition, and when we apply the far-field boundary condition, that tells us what this arbitrary function is. It's just a linear function, and it also tells us what the strength of the dipole is. And this is a plot of the width of that upstream flow as a function of the strength of the dipole. So the dipole has this strength here. There is no upstream flow. We just have actually a doublet at the origin. Then as we decrease the strength of the dipole, the maximum of the width decreases and slowly moves upstream. And in fact, you can get an explicit expression for the shape of the boundary. And as you would expect, near the stagnation point, it has a logarithmically infinite curvature, and that was something that Sala got many years ago. It's interesting. And here's some plots. Here's a plot of the velocity field. So these are streamlines for the steady flow. Here's the shape that we just found. These are streamlines obtained from integrating the velocity field. So near the origin, it looks like a dipole with this cyclonic, or this clockwise circulation, and then away from the origin, the vorticity takes over and gives us this uniform current. Okay. So that's a model. It has weaknesses. In particular, we've left out the density effects, and the density could well be the dominant thing. There will be parameter regimes where it's the density that sorts the flow out and not the vorticity. And so let me quickly come back to how we could solve the density problem. And that is, let's bring back the density, but let's make the long wave approximation. The waves were long. Here's our interfacial condition. This is just says that that surface is a material surface. So that just says if you advect the surface along the surface, you get 0, and that can be written as this equation here. Now we've made the long wave approximation, d by dx falls out of our governing equation. So the governing equation is just an ODE with x and t appearing parametrically. So we just solve this and stick it into here, and we have a first order PDE for the evolution of the surface. And maybe I'll jump quickly. You can now solve that analytically. And let me jump through and let me show you some analytical solutions to that. The interesting ones are when the PV is negative, because then the vorticity is trying to drive the flow in this direction, but we now have a Kelvin wave in the problem which is trying to drive the flow this way. And so the flow, actually in this case for very weak vorticity, is uncontrolled, and the fluid that just comes out of the source just continues to go outwards. And I can show you a movie of that. So we're driving fluid out with uniform velocity out of between -1 and 1. We get an upstream rarefaction here, and we get a downstream rarefaction, in this case led by a shock. If we make the vorticity a bit stronger, then in fact the flow becomes controlled at the so-called downstream edge. The control then propagates across the source region until it hits the upstream edge of the source region, and then it gives us a constant width current led by a rarefaction and a shock. If we make it even stronger, then actually the dynamic stays the same. The only difference is that we have a full height shock once the shock develops. And that's the one that's approaching the rigid lid limit. That was the one that had a full height shock. So let me jump to my conclusions. Well, let's see if we can apply it to the laboratory. If this stuff I've just shown you is relevant, then it says that the first thing to note is nobody tells you when they do experiments. No one measures the vorticity. No one tells you what their PV is, so we have no idea what the vorticity is in the experiments. And the same with the numerics. People don't seem to bother to compute the vorticity. And so we have to guess what's going on. We assume it's probably about zero total vorticity, so large negative relative vorticity in the experiments. And that's the case we just looked at. And that suggests that this outflow is an unsteady rarefaction, and that therefore the strength of this outflow is set actually by a critical control that we saw at the downstream edge of the blob. So just to say what we've hopefully seen, that you can make simple nonlinear models of these outflows. You can combine Kelvin wave dynamics with the vortex image driving. That when I didn't have a chance to show you this, when there's the reinforcing dynamics, that the vorticity and the Kelvin waves go in the same direction, there's really no upstream flow. And we get these controlled solutions. The ones we looked at were negative PVA. They had the opposing dynamics. If the vorticity was weak, then the upstream flow, we got uncontrolled flow, and the flow just spread outwards without limit. As we strengthened the vorticity, the flow became controlled at the downstream edge and gave us a finite width downstream rarefaction. And I didn't show you, but what happens when you compare it to the full integrations, then you find that the dispersion starts to affect the current widths for a point source. You're not surprised at that because the point source is extremely narrow and we made a long wave approximation. If we try and improve it by making the source wider, then in fact we find that finite amplitude waves appear in the flow. Okay, thanks very much. Yes, it would be. Now, I don't know any observations near there, but you're quite right. I mean, this is dominated. We need the Coriolis force to be dominant. So near the equator, where F is 0, then yes, you'd expect some other thing to happen. Absolutely. Yeah.